Okay, we are back and we need to move forward. So on the last video, we were seeing how to do this operation, multiply these three matrices, and we did with octave, and we gain time. Um, what was important was to see that multiplying these three matrices is evaluated um, this matrix, which is the matrix which represent rho, pitch, and yaw, the angles. So this is the rho, pitch, and yaw matrix. Rho, pitch, and yaw. So this is all that we done on the last video. And if I'm not wrong, two or maybe three videos, on the past three videos, um, we were constructing this transformation equation, which is from the rotations of rho, pitch, and yaw. These angles they are angles of rotation. So right here, so I was explaining how you can construct this matrix. So I said that is based on the characteristical transformation matrices above the y, z, y, and x axis. And I said that z is for A because it's pointing on the same direction, and I write this here, and you also can find this on the book. So A is pointing on the same direction as Z, so we use the characteristical transformation of rotation above the Z-axis, and we just have to adapt this characteristical transformation of rotation matrix of rotation, this characteristical matrix of rotation. We just need to adapt it to with the angles phi A, and for the we have three axes making the three-dimensional space. So we have the n axis, which is from this is a framework, okay, or a reference frame. Right here, I'm not linking this framework or reference frame to the origin of this referential system, or also a reference frame, because I'm doing just like on the book, and on the book is illustrated this way. So n is pointing on the same direction as the x-axis, so we just need to get the characteristical matrix of rotation above the x-axis and adapt with the angles. So right here is phi n, and for the O matrix, which is the matrix of rotation above the O axis, we just need again to adapt to the characteristical matrix above rotation that is made above the y-axis, the characteristical rotation matrix. Okay, so those are three. Um, this first matrix is for the angle of rho, which is above the a-axis. The second one is from the angle yaw, which is above the n-axis, and this one is from pitch, from the rotation of pitch, from the angle of pitch, so is above the o-axis. So when we apply these three transformations of rotations, or you can just say just rotation. Till here, I'm always saying transformation of rotation, transformation of translation, because they are transformations, but you also can just say rotation or translation. Okay, so applying these three angles of rotation, we can write this RPY matrix and also write this transformation equation. Okay, and as both of these matrices with these respective angles are defined, so RPY also is going to be defined. And I was saying that is another technique that we apply to, for example, restore some position or some orientation. So as each element on the matrix, it represents something on the three-dimensional space, these matrices, when we have matrices and we prime multiply or post multiply, is usually to on robotics, on directly robotics application, is with the object of restore a position, a motion, or even change the position and also, sorry, position and orientation, or even change the position and orientation. So this is the object of multiply a matrix, and it makes sense. It is very intuitive. We are multiplying it can be another matrix which is representing the initial position and orientation of a robot, independent the number of the degree of freedom. Is very intuitive that if we multiply by another matrix, we will change the position. And right here, we are doing this to restore a position or change some position and orientation as well. Okay, with that being said, we need to go on. And okay, so I'll use the content of the book to move forward with this explanation. So this matrix that you are seeing, it represents the orientation change caused by the RPY. So right here, obviously, we are multiplying. One of these is representing the rho angle. Another is representing the pitch, and other is representing the yaw. And these are rotations. So when we multiply, we obtain this RPY matrix. And what is going to do is to change the rotation. So I will keep reading the explanation of the book. So the location and the final orientation of the frame relative to the reference frame will be the product of the two matrices representing the position change and the RPY. So what does that mean? Um, is this statement that I have just read is like already introducing a content because it doesn't mention I need to read the rest, but this first part of this statement, it doesn't say that is already multiplying by another matrix, but is exactly what I was saying before. Um, any position, we can take, we can use this, and but this one with a vector on the origin of the XYZ system, which can be a reference system, and this vector in yellow can be a robot arm as analogy. So here it can be represented by a matrix. So we can do this. So, but what system is this? I draw right here a cylinder, but let's just make easy. Let's say is a coordinate system, is a reference frame, the unknown reference frame XYZ, and we can represent this. Let's say on this, let's say is the Cartesian one, Cartesian coordinate system. So on the Cartesian, we know that we will just have ones for representing a motion. We will just have ones on the main diagonal of this matrix. And the last column is representing the position. So it's Px, Py, Pz, and 1. Okay, see, we can easily represent a robot on a 3D space, on a system in which is localized with matrices. And this statement that I have just read to you, this statement, the location and the final orientation of the frame relative to the reference frame will be the product of the two matrices. Right here, the product of two matrices in a frame relative to the reference frame. So right here, again, let's use as example. Right here is the frame, and right here is the reference frame. And again, so if we wanted to change this position, and I don't know if RPY matrix it can be applied to a Cartesian coordinate system with this matrix, but the idea that this statement is bringing is if you wanted to change right here this position, this orientation, we do multiply by RPY matrix, and the final position and the final orientation of this framework are, well, again, this is a reference frame, but this one is also a reference. Okay, so okay, let's call framework, but it is also a reference frame. Okay, its final position and orientation will be given by this product. Okay, see, so that is what this statement is, is telling to us. Okay, so let's keep going. And it gives us a example. And we need to suppose that a robot is designed based on spherical coordinates. That's cool. Now we will change the example. We were doing an example with on the Cartesian coordinate system, and now we are on the cylindrical, no, spherical coordinate system, and RPY. Then the robot might be represented by, okay, that's easy. We just need to write a general transformation equation. So I will write this example. So the example is, let's suppose that a robot is designed based on spherical coordinates and RPY. Okay, we don't need even draw the a draw with a cylinder and representing its coordinates. And right here we will just need that, and it already gave us a H frame in relation to the R frame. It's just the cylindrical coordinate system, and again, RPY matrix is a matrix that we multiply, for example, to restore or change the position orientation of a robot. So I will take the coordinate system, spherical. Is this spherical, not the cylindrical? So right here, for example, we are on this reference frame, or just framework, whatever you want to call this, because again, at this point, you need to recognize a lot of terms, and as this one is also a reference frame, so okay, I need to explain that to you. So let's say that is a robot, is the robot hand. So I will copy this, and I think it's going to work. Okay, so I will copy, nice, and paste right here to use as example. So right here, let me place this right here. That's nice. Okay, so this is right here, we can attach it a robot hand, which is the frame H. And right here is the reference frame R. Nice. So um, look how good it is. We without any task description, without any description, we can already write a transformation. So is a transformation of the frame H in relation to the frame R, because uh, this frame it turns into a reference for this frame, and I already has explained this to you. Um, because of this, we can write transformations because we use another segment of the robot or a reference, and we call this reference to write a transformation. Okay, so let me just do this smaller so I can write the transformation equation. So the example is, let's suppose that the robot is designed based on spherical coordinates and RPY. Okay, and the statement that I read, but I don't write. Let me repeat uh, again. The location and final orientation of the frame relative to the reference frame will be the product of two matrices representing the position change and the RPY. So right here, this product is this whole motion which this robot is doing is the product between the matrix representing the transformation representing the total um, transformation of the spherical coordinate system with the angles beta and gamma multiplied by the RPY matrix. So RPY is a matrix, not a transformation. So we got a transformation, and when we multiply by RPY matrix, we are restoring or changing the position in orientation, as I'm keep reading, keep saying. Okay. Is phi A, phi O, and phi N. Okay, so let's say we wanted to change this point right here. I don't know, for in spherical we have a great precision. It is a system very created, so we can put this in the factor with this attached to, which can be a hand, any tool for grab, and we can put right here, and on the any space which is on a sphere, any point that we can represent on a sphere. And I don't know a sphere if you start with the smaller point as you wish. So yeah, with spherical is one of the most or the most accurate system for a robot. So this you apply in any type of joints. So imagine this this mechanism in a joint. Now imagine you are tracking this mechanism and doing a control to reposition something robotics, okay? And that's nice. So we have just write the transformation equation, which represents the final position and rotation on the spherical coordinate system. And applying RPY matrix is a technique to change or repositioning, restore the rotation position. Okay, let's keep going. Okay, so I will keep reading. The inverse kinematic solution for RPY is more complicated than the spherical coordinates because here they are three coupled angles where we need to have information about the sines and the cosines of all three angles individually to solve for the angles. To decouple these angles, we pre-multiply both sides of the equation by a rotational above A with phi a is inverse of the rotation above A, and we have just we already has applied this technique, which is do a rotation above the A on the frame A NOA, and this is going to be very nice because I will track this concept and show this concept that we have just applied and we are applying again. So this is going to be nice. So first let me explain this statement that I have just read to you. Okay, it starts with inverse kinematic solution. Okay, remember that we were seeing inverse transformations. So we can have a rotation on any axis. It can be of the reference frame or framework N or A, or it can be the coordinate system or reference frame X, Y, Z. And for any of these axes with any angle, we write the superscript -1 in kinematic solutions. It's used to just exactly restore or change positions. So remember I was saying, and this is I don't know, on the first videos, when we are working with forward kinematics equations and inverse kinematics equations, we work with them both together, and one of them is going to tell to us where the end effector, where this robot is localized, and the other will basically tell to us where we wanted to our joints, where we wanted to our links are localized on the 3D space. So forward it is going to tell to us where it is, and inverse where we want it to be. Okay. So it starts with inverse. So the inverse kinematic solution for RPY is more complicated than the spherical coordinates, because here There are three coupled angles, so is phi A, phi O, and phi N, where we need to have information about the sines, cosines for the three angles individually to solve for the angles. Okay, and now I will look for the information. We will, in order to solve this, we will multiply by a rotation above the a-axis with phi a angle, and we will apply this inverse transformation. And again, inverse transformations from we used to solve a transformation equation because we wanted to know not just where it's going to be or in the factor, but also where we wanted to put each link and joint in the factor, the whole system of the robot. So it's telling to us to multiply by this rotation, but it's not coincidentally. So I will look for the example in which we were applying this same technique. Okay, so let me look for them. Look for it. Right here. Look how nice it is. Restoring the original orientation position of the frame NOA. We can restore the original orientation of the reference frame by rotating the NOA frame around the A-axis. See, it's not coincidence. It's a technique that we have just learned and we are applying again. And for what? To restore the original position and rotation of the frame. We are getting closer, getting close. I think it's this. Okay, so okay. Okay, so first let me just complicate this because again is the inverse kinematic solution for RPY, and so let me write this is the inverse kinematic solution for RPY. Okay, so we just have write this transformation equation, and now we will work on its solution. So again, let me write this inverse kinematic solution for RPY. Let's apply the technique applying the technique, applying the technique. So um, to restore orientation, applying the technique to restore orientation in position. So we do a transformation of rotation above the a-axis with some respective angle, and sometimes is minus alpha. Okay, let's see. Um, so what we're going to do is multiply both sides, and it's not only multiply right here. Remember that the order of the transformations, which will be resumed on the order of the matrix, it matters, and this will influence on the final result. So we have post, we can post multiply, or we can have pre-multiply, which is by the left and by the right. Okay, so right here we will post multiply, so we will multiply because we want to solve this transformation equation, and we are doing the kinematics analysis. So let me write this also. Kinematics analysis. So is doing the kinematics analysis. Okay, nice. So we will post multiply by a rotation, inverse transformation of rotation above A with phi A angle. I keep saying phi, I will say phi angle inverse is a inverse transformation. Inverse transformation of rotation. Inverse transformation of rotation. And we will multiply on both sides RPY matrix O and N angles phi O and phi N. Now I will copy this to buy some time. Let me make this smaller because we need some space. Ah, too big. Let me just copy this. And perfect. Let me make this smaller. And now, obviously, these terms will cancel each other, and we are left with the respectively matrix. Sorry, transformation equation. We are left with the following transformation equation, which we solve it using kinematic analysis. And let me write this: kinematics analysis. Basic, where we want put the links in joints. After doing the transformation, I think is best. Doing the transformation. Okay, and is what we have just made right here. We have made it a kinematics inverse, not only a inverse kinematic. Okay, what else? Okay, let me read the statement. To decouple these angles, we pre-multiply. I said post? No. Yeah, I said post. So right here, let me change by the left, by the right. That can be confused. Right here by the right, and right here by the left. We are pre-multiplying. Okay. So it's not just as I'm seeing. I think already have said that to you. Right here, we are restoring the orientation position, but also in between this process, within this process, we are decoupling. Let me see if is this. I think it's this. We are decoupling the angles. So when we multiply by a rotation above the a-axis of the reference frame, and this is not coincidence, you are doing this on purpose. So is the axis. We are not doing a rotation above n or o axis. We are doing a rotation above the a axis. So is proposal is for propose. Um, and when we do this, we can restore the position and orientation. And within this, we are decoupling these angles. So is the process, in between the process. And now we will keep introducing concepts. Assuming that the final desired orientation activated by RPY, again, um, listen to this. Assuming that the final desired orientation activated by RPY, again, is a matrix that we multiply by another matrix, and of course is a matrix which is representing a rotation or a translation. And I'm not so sure if this matrix of RPY is applied on transformations of translation, but as you can see, we are applying on transformations of rotation. So on the matrix of the transformation of rotation, we apply this RPY matrix. In this way, we get our desired position, or we can restore the old orientation position. Okay, so assuming that the final desired orientation activated by RPY is represented by NOA matrix, we have, so right here we are introducing this concept. We are assuming the RPY matrix is it can be represented by another matrix. So right here we have to reuse this equation. We are keep going with our analysis. So is rot above A with some phi A angle is inverse transformation, and this matrix we will assume that is another matrix, and we will analyze this. Why this? Because I'm also learning at the same time as I explain this to you. So let's see why. I'm very curious about it. Okay. Okay. N is equal. Let me place this a little bit down right here, and this one, this term I'll look up. Okay. So let's see. Okay, so this matrix is representing right here. What I will write is the statement that I have just read, assuming, because this matrix, it is what this statement is saying to us. We will assume that we can skip this. Let me just write, assuming that the final desired orientation, final desired orientation So let's review what we were doing. We are doing a inverse kinematic analysis, not just a kinematic analysis, is inverse. Okay, inverse using inverse transformations. Okay, so again, let's suppose that a robot is desired based. No, I do not write this statement, but is um, let me find again right here the location and the final orientation of the frame relative to the reference frame will be the product between of two matrices. So we were multiplying uh, the original equation is this, and the example, okay, is with the spherical one, this one, but we skip this and introduce more concepts. Okay, so desired position, final desired orientation, we can say by the elements, because right here we have this reference frame, NOA, whatever, and link it on other reference system, maybe, probably Z, Y, X, and as you can see, in N referenced to X, O referenced to X, A referenced to X, and so on and so forth. Okay, and we are almost there, almost finished this explanation, and the rest we'll have to do some operations. Okay, we are doing this. It was best if I have if I have write it this statement, but we are doing this in order to solve for the angles of PA, O, and M, because the angles is what give us the orientation. Okay, so not the angles, cosine and sine, so you can have a clue. Okay, so just by reading this transformation equation, and if you uh, see right here cosine and sine, you can already guess this is something related to the orientation, because position we decompose when we have cosine and sine, we decompose on x, y, z components, but so this is for orientation, and for position we just place the points, place um, the scalars on this coordinate system, which is the Cartesian one. So this way we are kind of drawing a trigonometric figure on the 3D space. And for orientation, we are working with sine and cosine, and we decompose for x, y, and z components, and this way we will writing a trigonometric figure on the three-dimensional space. So if this is a robot, is going to do like the motion that is going to do, it will look like, of course, we are not drawing nothing, but I hope you got it. Uh, and we are solving for, we are solving for the angles rho is rho or rho is PA, I don't know, in pitch. Pn, I don't know, in yaw. Pho. And this is will give orientation. Okay. And again, now we will multiply. Let me copy this. We will multiply these matrices. And this is going to be a good exercise. Did you know what is the rotation matrix? Right here, the only problem is with the superscript 1, -1. But I think we can skip this. And let's see. We know that Z A is pointing on the same direction as the Z-axis. So let's take the right here. It's perfect. So let's see if it's really this. And the book, it doesn't bring this, but let's say is this. Okay, and we will have to multiply by this matrix. And is equal now. Yeah, the only problem here is this -1 superscript, and I don't know if we will use the octave again because this is a very large operation, very laborious operation. But let's just assemble this equation, this operation. So let's see the rotation above the O-axis. Right here, the rotation, and above the x-axis, sorry, above the n-axis. O and N. Okay, that's it. And we do multiply, we solve again to find, we solve to find A F A F O M F N. Okay, so this video it takes is already very long, and I will find these angles of row and pitch in your the next video using the octave. Um, so for now it's all. It was a very long video. Hope you got it. All that I wanted to explain. This is, I think, is the third one of this row pitch in your angles, and hope you like it. And for now is all. That's it. Thank you.